thank you. Thanks to all the members of the jury, and thanks to all of you to be here to attend my PhD defense. My PhD that is titled Optimizing Data Leakage Exploitation in Streaming Channel Attacks. And I realized this PhD under the supervision of Maxime Pelka, Amand Afka, and Ruben Salvador. So in everyday life, we are using electronic devices like a laptop, mobile phone, and all of these devices, they are handling data that we want to keep confidential, like pictures, messages, and any kind of device data. And all of these devices, they are connected to each other in order to share this data. And to do that, they are using communication channels like internet and wireless channels like Wi-Fi or Bluetooth. And the danger with these communication channels is that an attacker can listen to what we are transmitting over these channels, and then an attacker can recover our data. So before to transmit this data over these communication channels, we first need to protect them. And to do that, we are using cryptography. So imagine that we want to transmit a set of images over an unsecure network to a legitimate receiver. So the images are the data that we want to keep confidential. We call them the plain text. And in order to protect them, we are first going to encrypt them using a secret key to get what we call the ciphertext. This ciphertext, an attacker can access them, but it's not a problem since it's impossible for an attacker from the ciphertext to recover the initial plain text without knowing the secret key. Only a legitimate receiver can decrypt the ciphertext in order to retrieve the initial plain text when the legitimate receiver has the secret key. So now all the secret is handled in the secret key. And one very frequently used cryptographic process in everyday life is AES. So AES stands for Advanced Encryption Standards. It's a standard of cryptography that we are all using every day. And with AES, the secret key is composed of bits. So one bit can take two values, 0 and 1. So with one bit, we have two possible keys. And as we increase the number of bits in the key, the number of possible keys increase exponentially. And in AES 128, there is 128 bits. So there is billions of possibilities on the key. So even if the attacker could try billions of secret keys per second, it would need more than the edge of the universe in order to recover the secret key that can allow to decrypt the ciphertext to retrieve the plain text. But these cryptographic processes, they are computed on electronic devices, like a processor, for example. And this, from a hardware point of view, these devices, they produce what we call side channels. These side channels can be, for example, disturbance in the power supply or electromagnetic emanation due to the internal electrical activity of the device. And it is possible to measure these side channels. Here, for example, we have a setup where we are measuring the electromagnetic emanation from a device as it computes some processes. And because these side channels are produced by the internal activity of the device, it is possible to analyze these side channels in order to recover some internal data. For example, imagine that our processor is computing an AES cryptographic process. Then one of the internal data is a secret key. And as the victim computes an AES cryptographic process to encrypt a plain text, the attacker can collect what we call a trace, which corresponds to the measurements of the leakage produced by the victim as it computes the AES. And in a side channel attack, the attacker is going to collect multiple traces as the victim computes multiple encryption to encrypt multiple plain text. And at the end, because all the traces contain information on the same secret key, it is possible for the attacker, by analyzing these traces, to recover the value of the secret key. But a limitation in the side channel attacks is that we need to be at proximity of the victim device in order to be able to capture these side channels. If the attacker is at a distance from the victim, it becomes theoretically impossible to capture these side channels. And here comes the interest of what we call the streaming channel attacks, in which the streaming channel attacks are a specific case of the side channels in which we have an additional element that is going to transmit the side channels at a further distance. So at what kind of device can this attack happen? This attack has first been demonstrated in 2018 by Giovanni Camorati and Hall on a mixed signal device, which is the NRF from Nordic Semiconductor. So a mixed signal devices means that on the same silicon die, we have a digital part that is going to compute the cryptographic process and a radio frequency module that is going to be used to transmit legitimate signal. And this kind of device is very frequent in IoT devices, as on these devices, we need to integrate multiple systems into the same silicon die in order to save power, cost, and space. And this kind of devices represent today 19 billion of devices, and this number should only grow because it should double by 2030. And what is going to happen on this device is that we have the RF module that is designed to transmit a legitimate signal, for example, a Bluetooth signal at 2.4 GHz. But here, the side channels that we described just before are going to reach the input of the radio frequency module, and this one is going to involuntarily modulate, amplify, and transmit these side channels at a distance of few meters. Then the initial side channels, which happen at every harmonic of the digital clock frequency, are going to be modulated around the frequency of the legitimate signal. And an attacker can collect this leakage at these frequencies and then perform a conventional side channel attack at a distance of few meters. So here is the setup that we are going to use in our experiment when we perform the attack by cable. So we perform the attack by cable when we want to avoid the pollution from the environment. Here we have the victim device. We have the attacker that is collecting the leakage at the output of the RF interface from the victim. And when we want to perform an attack at a distance, we have the same setup, but using a directional antenna in order to capture the leakage from the victim at a distance of few meters. So when we perform an attack, we do not always manage to recover the correct value of the secret key from the information we collect in the screaming channels. Instead, what we can do is we can rank all the possibilities on the secret key from the most probable to the least. And then we can look at what we call the key rank, which corresponds to the rank of the correct key we are searching for among all of these possibilities. And in a side channel attack, as we increase the number of traces that we collect during the attack, we expect this key rank to decrease. In the best case, we expect the key rank to be equal to 1. It means that we have recovered the correct value of the secret key. But if it is not, it is still possible for an attacker to test multiple hypotheses and check if one hypothesis on the secret key is correct or not. To do that, we use a brute force attack. So in a brute force attack, we make the reasonable hypothesis that the attacker knows at least one plaintext from the victim and the associated ciphertext. Then, to test if one hypothesis of the secret key is true or not, we encrypt the plaintext, we get a ciphertext, and we check if this ciphertext equals the one from the victim. If it does, it means that the hypothesis corresponds to the correct value of the secret key. Initially, we will not more than the edge of the universe to perform a brute force attack. But as the key rank is going to decrease, the brute force attack is going to be feasible in a reasonable time. For example, with our experimental computer, which is a standard computer, when the key rank equals 2 to the power of 41, we can brute force the key in 1 week. And when I will give the result of our experiment, I will not speak of the key rank, I will speak of the Gaussian entropy, which consists only to keep the power 2 of the key rank, and the time to brute force the key is going to decrease exponentially as the Gaussian entropy decreases. So in this state of the art, after the initial paper that demonstrated that we can recover an AES key from the leakage transmitted in the screaming channels, Giovanni Camurati and Paul studied this attack on different implementation of the AES. For example, a software implementation of AES we compile with optimization, or an hardware AES. They also studied this attack in different environments and distances, and they managed to perform the attack at a distance of up to 15 meters. Then, following works are studied the use of analysis attack in order to, based on deep learning, in order to reduce the number of traces that we have to collect to perform the attack. And this can be very convenient when a victim computes a few number of cryptographic processes. And in this thesis, we are going to first handle the challenge to collect traces at a distance. Then we will study the frequency diversity property of the leakage, the fact that the leakage is present at multiple frequencies. And this will be very convenient to attack in a polluted environment. And we will also use this frequency diversity property to propose new attack to combine multiple frequencies together in order to reduce the number of traces that we have to collect. Then we will study this attack on a stronger and more complex devices than the initial NRF device. So in this presentation, I will first present the 4 contributions that we propose during this PhD. And after this, I will finish with conclusion and the perspectives. So the first contribution concerns the challenge to collect traces at a distance, and all the results from this work were published in SIPS 2022. So when we perform any kind of such channel attack, we need to know very precisely when the victim is computing the cryptographic processes in order to know when to collect the different traces. To do that, usually in laboratory conditions, we have the victim to produce what we call a trigger signal, which is going to indicate when the victim is starting the cryptographic processes. And with this, the attacker can segment the leakage from the victim and segment the different traces. But in a screaming channel attack, we do not want to have a trigger signal. Why? Because the purpose of the attack is to be performed at a distance. So we do not want to put a wire between the victim and the attacker to transmit such a trigger signal. To avoid the trigger signal, in previous work on the screaming channels, they use another method that we call the frequency component trigger mechanism. Yes. And it consists in finding in the RF signal from the victim a frequency component where we have a signal that acts as a trigger signal. For example, here we can observe the signal from the victim. We have in the x-axis the frequency and in the y-axis the time. And in this signal, we can find a frequency component where we have a signal that changes of value once each time the victim starts an AES encryption. Then by collecting this frequency component, we can, by detecting the falling and rising edge, use this signal as a trigger signal. And when we use this method to reproduce the attack, we can observe here the attack performance. We can observe that the Gaussian entropy decreases as we increase the number of traces that we collect in the attack. And here we have good performance, and the Gaussian entropy reaches a value of 6. So this method allows to remove the need of a trigger signal in laboratory conditions, but it has some limitation when it comes to collect traces in scenarios that would be more realistic. And we are going to demonstrate this with 2 experiments where we are going to add some constraints that could happen in a more realistic scenario. The first one consists to add time variation. So in initial condition, we have the victim to compute multiple cryptographic processes recursively. And now we are going to voluntarily add random time variation between the execution of the different cryptographic processes. And when we do this, we can observe with the red curve that the performance of the attack is decreased. The Gaussian entropy increases. The second constraint consists to modify what we call the time diversity. So time diversity is something that we commonly use in such an attack in order to reduce the impact of the noise. What we do is we have the victim to compute multiple times the same encryption with the same input, the same plaintext and the same key, and then we average multiple traces together. For example, here is what we get when we average 10 traces together. So the impact of the noise is reduced. And as we increase the time diversity order, the impact of the noise is reduced. And when we perform the attack by reducing the time diversity, so initially we had a time diversity of 500, and when we reduce it to only 10, then it's not only that the attack performance is decreased, it's that the attack does not work at all. Probably that when the victim is computing only 10 cryptographic processes, it does not even produce such a trigger signal as a frequency component. So the method to segment the traces does not work. In order to remove this limitation, we propose to use another method to collect the traces. And this method is a pattern recognition. So for pattern recognition, in a profiling phase where the attacker handles a similar device as the one from the victim, we are going to keep using the initial method, the frequency component method, because in a profiling phase, we can make sure that there is no time variation and that we have a good time diversity order. So we can still use the initial method to collect one trace that we are going to use as a pattern. Then during the attacking phase, we have the victim that computes cryptographic processes. Here we can have time variation and the victim can compute a series of processes with a low number of processes. And what we are going to do is to compute the sliding correlation between the victim's leakage and the pattern in order to detect in the victim's leakage where are the position of the pattern. And by doing this, we can segment the victim's leakage. And when we perform the same experiment, but using pattern recognition, we can observe that we remove the limitations from the initial method. Here, both in initial condition and with time variation, we get the same attack performance. And with the reduced time diversity, of course, the attack performance is decreased, but it's also because we decrease the time diversity order. So we reduce the noise reduction. And we could compensate this by increasing the number of traces that we collect. So to perform pattern recognition, we are still using the initial frequency component method in a profiling phase to extract the pattern. The problem is that this method also has limitation in the profiling phase. First, we suppose that the victim is producing such a frequency component, and it will maybe not always be the case against any device that we want to attack. Second, we need an additional tool, which is a spectrum analyzer, in order to detect the frequency component. So in order to remove this limitation, we propose to use another method to extract a pattern in a profiling phase, and this method is called the virtual trigger. To understand the concept of the virtual trigger, let's consider that this line corresponds to the leakage produced by the victim while it computes a series of cryptographic processes. Each segment corresponds to the leakage from one execution of the AES. So with the virtual trigger, we make the hypothesis that the time duration of one cryptographic process is always the same. And under the hypothesis that it is computing without interruption, if we know precisely enough the time duration of one cryptographic process, then it is possible to segment the initial row trace by cutting it in segments having this precise length. Then we are going to get segments that are similar to each other, and by averaging them together, we'll get a trace that we can use in pattern recognition as a pattern. But the difficulty with this method is that we need to be very precise on the knowledge of the time duration of one cryptographic process. Otherwise, we won't segment correctly the initial row trace, we won't get a length segment, and we won't get a good pattern. So in order to find the precise length that we can use for virtual trigger, what we propose to do is to test a range of candidate lengths and to evaluate if one candidate length is precise enough to be applied for virtual trigger. What we do is we segment the initial row trace with this candidate length. We get multiple segments. We take half of these segments that we average together to get a segment of reference. We do the same with the other half. And if the candidate length is precise enough, we will correctly segment the initial row trace. So the two segments of reference should be very similar. And the L1 distance between the two is going to be low. On the contrary, for every other candidate length, we won't correctly segment the initial row trace, and then the L1 distance between the two segments of reference is going to be high. And when we apply this method over a range of candidate lengths, we are going to find the most precise length that we can use to apply for VT when the L1 distance is going to reach its lowest point. And there is an additional advantages of using the virtual trigger compared to the initial frequency component method, which is the virtual trigger is going to work at every frequency where the leakage is present. To demonstrate this, we apply the two methods at another frequency than the one used in previous work on screaming channels, but we avoid to perform any additional manual step, like searching for a new frequency component, for example. So at the other frequency, we are using the same parameter in order to filter the frequency component. And at this other frequency, the frequency component does not contain a signal that can be used as a trigger signal. So the initial method does not work properly. But the virtual trigger is based on the knowledge of the time duration of one AES execution, and this does not change from one frequency to another. So we can still use the virtual trigger at another frequency than the initial frequency. So to conclude on this work, we handle the challenge to collect traces at a distance. We started with the initial method proposed in previous work that work in laboratory conditions, but we demonstrated that it has some limitation when we add some constraints that can happen in a realistic attack. To remove this limitation, we propose pattern recognition. But in order to use the pattern recognition, we first need to have a pattern. And we can still use the initial method to extract a pattern. But this method also has limitation in the profiling phase to extract a pattern. So in order to remove this limitation, we propose a virtual trigger, which has the same limitation as the initial method in a realistic attack, but which removes the limitation in the profiling phase. So after this initial contribution, we wanted to study the frequency diversity property of the leakage. So the fact that the leakage is present at multiple frequencies. And this will lead us to the two next contributions. So as I said, when I presented the screaming channel attack, the leakage is present at every harmonic of the digital clock frequency around the frequency of the legitimate signal. And in all previous work on screaming channel attack, they use only the second harmonic. Why the second one? Because the first one is often polluted by legitimate signal, like Wi-Fi or Bluetooth. And the further we go in frequencies, the weaker is the leakage. So the second one is most of the time the more interesting one in order to mount a successful attack. Then we have the question, which is, what happens if we collect the leakage at different frequency and we try to combine them together? Could we try to improve the attack performance? So we performed an experiment where we collected the leakage at the 4th harmonic, and we collected the leakage at a distance. And what happened is the leakage was the two first frequencies were too polluted to have a successful attack, and the fourth one was too weak. So first, we did not have frequency diversity because only one harmonic was good enough. And second, one important question came, which is, what would happen in a polluted environment where all the harmonic would be polluted? Does it make the attack unfeasible, or could we try to keep the attack feasible by using other frequencies than the harmonics? And from here come our second contribution, where we are going to study this attack at other frequencies than the harmonic. And the result of this work has been published in CARDIS 2023. So we can expect that the leakage will also be present at non-harmonic frequencies, because previous work on mixed signal devices demonstrated that when the digital part produces a leakage at one given frequency, for example, 10 MHz, then when this signal will go through the substrate will act as a filter, which is going to spread the leakage over a wider range of frequency. Then in the RF front end, it is possible to retrieve energy from this signal at other frequency than the initial harmonic. And now, if we look at the output of our victim, we can see here the peaks that correspond to the legitimate signal, the Bluetooth signal at 2.4 GHz. We can clearly see the 4 peaks that correspond to the 4 first harmonics, but there is also energy between these harmonics. So one question is, can we demonstrate that the leakage is also present at non-harmonics and not only at the harmonics? And if leakage is also present there, a second question is, how difficult is the attack using non-harmonics compared to using harmonics? So to answer the first question, which consists to evaluate the leakage presence over the spectrum, what we propose to do is to use a method commonly used in the search channel community to do leakage assessment, which is a t-test. And we are going to perform this t-test over a range of frequency going from minus to plus 1 GHz around the frequency of the legitimate signal. So from 1.4 GHz to 3.4 with a resolution of 1 MHz. Then at every frequency where we evaluate the leakage present, what we are going to do is, first, we will extract a pattern using the virtual trigger. We need to do this at every new frequency because the shape of the leakage changes from one frequency to another. Then, with this pattern, we will perform pattern reconnection to extract 1,000 traces at every frequency to perform the t-test. And the version of the t-test that we are applying is the fixed versus fixed t-test. So here is the result of the t-test according to the frequency where we perform the experiment. And the solid line corresponds to the frequency of the legitimate signal. The blue dotted line corresponds to the position of the harmonics, where we are expecting to find the leakage. And in order to conclude that leakage is present, we need the result of the t-test to be above the red line. And what we can observe is that the leakage is present continuously over the spectrum around the first harmonics. So with this experiment, we demonstrate that leakage is not only present at the harmonics, but also at the non-harmonic frequencies. But to perform this experiment, we needed we needed 52 hours. And here, the reason is that at every frequency, we have to collect a given number of traces. Here, 1,000 traces was enough. It was enough to collect 1,000 traces at every frequency to have a positive t-test. But on much more complex devices, sometimes we could need to extract tens of thousands or even millions of traces in order to have a positive t-test. So this is the limitation of using the t-test to do this test. So in order to remove this limitation, we propose another method in order to detect the leakage presence over the spectrum. And this method is going to remove this phase where we have to extract a given number of traces. This method, we call it pattern detection. It is based on the same concept as the virtual trigger we are using to extract a pattern. But here, we are not going to extract a pattern. We are going to evaluate our capability to extract a pattern. Because if we are capable to extract a pattern at a given frequency, it means that the leakage is present. So to do pattern detection, we suppose that we already know the time duration of one AES cryptographic process. At the selective frequency, we extract a raw trace. We segment it with the time duration that we have. We get multiple segments. Here again, we split half of the segment in one group that we average together. We do the same with the other half. And if leakage is present, the two segments should correspond to a trace and the correlation between the two is going to be high. On the contrary, at every frequency where the leakage is not present, the raw trace is only going to contain noise, and the two segments of reference will also be noise, so the correlation between the two will be low. When we apply this test over the same range of frequency as we did for the t-test, here is the result that we get, and we can observe that the correlation is very high around the first harmonics. In order to make sure that this high correlation is due to the presence of the AES leakage, we perform the same experiment, but with the victim not computing any AES. And we get the red curve. With the red curve, the maximum of correlation is around 75%. So we can put as a condition that the correlation has to be at least equal to 75% in order to conclude that leakage is present. And with this condition, we can compare the result from the t-test with the pattern detection. Here we highlight in green all the frequency where the leakage has been detected as being present, and we can observe that the two methods can detect the leakage over the same range of frequency. But with pattern detection, we needed less than 1 hour to perform the same experiment, so we save a lot of time. So with these two methods, we demonstrated that leakage is not only present at the harmonic, but also at non-harmonics. And now we want to go to the second question, which is, how difficult is it to success the attack using non-harmonics compared to the attack using harmonics? And to do this, we are going to perform experiments where we select a range of 150 frequencies where the leakage has been detected as being present. This range of frequency includes 3 harmonics, and we are going to perform at every of these frequencies the same attack using the same number of traces, and we'll compare the attack performance. And we'll do this experiment in 3 conditions. First, by cable to avoid environmental pollution, then at 2 meters, and then at 7 meters. So in the first experiment, we can observe the attack performance according to the selective frequency. We highlight in green all the frequency where the gain entropy is lower than 32, in blue where it is lower than 35, and all the other one in red. And the harmonics are highlighted with the red point. And what we can observe is the attack perform well continuously over the spectrum and not only at the harmonics. Then we perform the same experiment, but at a distance of 2 meters. And here we are losing the first harmonics and all the frequencies around because they are polluted by legitimate signal. But what is interesting is to observe that for every frequencies that are not polluted, the attack performs very well also at non-harmonics and not only at the harmonics. Then, in order to have valid results, we perform the same experiment, but by realizing 50 attacks at every frequency. And because we perform 50 attacks at every frequency, we reduce the number of selective frequency. We keep only the best one according to the result at 2 meters. And also the 3 harmonics. So we choose to perform this experiment at a distance of 7 meters. And at this distance, we also lose the second harmonics because it is too polluted to keep the attack feasible at this distance. As before, the third harmonics is not polluted, so the attack performs very well here. And what is very interesting to observe is that the non-harmonics that are not polluted perform as well as the harmonics. It means that if we were in a situation where all the harmonics would be polluted, we could keep the attack feasible by using this non-harmonic. This result is surprising because even though we could expect the attack to be possible at non-harmonics, we could also expect that it would be much more difficult at the non-harmonics compared to the harmonics. But here we can observe that we get similar performance. So after this work, where we study the leakage present at non-harmonics, we came back at our initial question on frequency diversity, which was, if we have multiple frequencies where the leakage is present, can we try to improve the attack performance by combining them together? And the result of this work is going to be published soon, submitted soon at Transaction on Information Forensic and Security. So before to study the effect of the combination, we first need to define a method to combine multiple frequencies together. So we start with our initial attack chain where we are using only 1 frequency. What we are doing in an attack is we collect traces. Then we have a phase where we reduce the dimension of the traces, either by keeping only what we call the point of interest, which are the sample in the traces that contain information on the secret key, or by using methods to do feature extraction, like for example, principal component analysis. And then we get point of interest or features, and they are analyzed in the analysis attack to return scores, which are probabilities that we use in order to rank all the possibilities on the key from the most probable to the least. Now, if we are collecting traces at different channels, so in our case, the different channels are the different frequencies, The question is how to combine this attack chain together. From this state of the art, the first method will be data fusion. So if we are collecting traces in parallel at different frequency, we could, for example, average the different traces together. And then we perform the remaining of the attack as if it came from only one frequency. The second method consists to extract feature from all the traces at once, and then we call this feature fusion. And the third method consists to average the score computed from the different analysis attack, and we call this decision fusion. In our experiment, we did not use feature extraction method. So we did not try feature fusion, but we tried and compare decision fusion and data fusion in order to observe which of these methods is the best, fits the best in the case of the screaming channels. And we observed that decision fusion fits better than data fusion. Why? Because decision fusion does not work at every frequency. For example, here in this experiment, we took the first frequency at 2.464 gigahertz, and we combine it with all the 150 frequencies where we collected leakage in the previous experiment on non-harmonics. And we can observe that at many frequencies, the combination does not return a good Gaussian entropy. When we perform the same experiment but using decision fusion, we get a reasonable Gaussian entropy all along the spectrum. So in the remaining of our experiment, we are going to use decision fusion in order to combine multiple frequencies together. So then the question is, how interesting is it to combine multiple frequencies together? And to do this, we'll first perform an experiment where we demonstrate the interest of combining multiple frequencies together, and then we will evaluate the improvement of the frequency combination according to the performance of the frequencies that we combine together. So in the first experiment, we take our 150 frequencies and we rank them from the best one, so the one with the lowest Gaussian entropy, to the worst one. And in order to make frequency combination interesting, we voluntarily reduce the number of traces that we are using at every frequency in order to have the best of the frequency with a Gaussian entropy of 50. With a Gaussian entropy of 50, we will need multiple months in order to brute force the key. What we do is we take the best of the frequency and we combine it with each of the initial frequency individually. And here is the result that we get from the different combinations. And with the best of the combinations, we get a Gaussian entropy of 42. It is still very high. We will need multiple weeks to brute force the key, but we are getting closer to a reasonable attack. Then we take the best combination and we combine it with each of the initial frequencies. And here again, we decrease the Gaussian entropy. And when we do this with 5 frequencies, we come from a situation where the key was not brute forceable in a reasonable time to a situation where we can brute force the key in few hours. So with this experiment, we demonstrate that frequency combination has an interest and can improve the attack performance. Now we want to study the impact of the combination according to the performance of the frequency we combine together. So in the first study, we look at the impact of the combination according to the performance of the frequency we combine together, and this for different level of performance. So in the first row, we are combining 2 very strong frequencies, and we can observe that the Gaussian entropy does not significantly reduce. While in the last row, when we combine weak frequency, we reduce the Gaussian entropy by more than 10. So what we observe in this first study is that the weaker are the frequencies that we combine, the more interesting is the combination. Then we perform a similar study, but with inequivalent frequency, in order to observe if the worst frequency can improve the attack performance or if it only decreases the attack performance. And in this second study, we can observe that combining inequivalent frequency is not a problem, since the performance that we get with inequivalent frequency is similar to what we get with equivalent frequency for 2 frequencies having a performance that equals the average of the 2 inequivalent frequencies. For example, at this line, we are combining 2 frequencies with a Gaussian entropy of respectively 40 and 50, and the performance of the combination equals what we get when combining 2 equivalent frequencies with a Gaussian entropy of 45. So the overall conclusion of these studies is that when we combine weak frequencies together, we reduce the Gaussian entropy. But it does not mean that combining strong frequency does not have any interest, because now if we look at the number of traces that we need in order to get a given performance, we can observe in every case that the combination reduces the number of traces. For example, here we are looking at the number of traces that the best of the 2 combined frequencies need to get a guessing entropy of 39. And this number of traces is equal to 50. And with the combination, to get the same result, we need 36 traces. So all of these studies on frequency combination were performed on 150 trace sets that we collected for the previous contribution, but they were collected at different time because we had one radio and the radio collected the trace set at one after the other. So in order to have valid results, we performed an experiment where we collected the leakage at two different frequencies at the same time and from the same cryptographic processes. So we choose to perform this experiment at a distance of 15 meters. And here, at the output of the antenna, we can observe that there is two radios. Each radio is collecting the trace at different frequencies. And the blue and orange line correspond to the result of the two frequencies individually. And the green line corresponds to the result of the combination. And the result of this experiment confirms the conclusion that we made on our previous study, which is combining multiple frequencies together allows to reduce the number of traces we need in order to get a given performance. And once the initial frequency have stabilized, the combination does not improve anymore the attack performance. So in the next and last contribution that we propose, we are going to study the screaming channel vulnerability on a different and much more complex device than the initial RF device. And in order to realize this work, I performed an international mobility of 4 months at KIT in the chair of dependable nanocomputing with Professor Mehdi Taouri and Dr. Denis Gnal. And this laboratory, one important line of work of this laboratory is remote side channel attack against FPGA. So the new device is the RFSoC, and RFSoC stands for Radio Frequency System on Chip. It's a system on chip from AMD Xilinx. Like any system on chip, we have a processing system containing multiple processors and a programmable logic part. And one of the particularities of the RFSoC is that it also includes a RF interface. And on this device, what changed compared to the RFSoC is that we have a very strong isolation between the digital part, the processing system and the programmable logic, and the RF interface. Because even though all of these modules are on the same package, they are actually not on the same substrate. The substrate is divided into different parts in order to isolate all of these parts. Also, they do not share the same power distribution network. And another very important difference between the RFSoC and the NRF is that they do not have the same radio architecture. I will not go into details in the difference, but one important element to remember is that on the NRF, we had an analog mixer which modulates the leakage from the digital part around the frequency of the legitimate signal. While in the RFSoC, we have a different radio architecture that does not include such an analog mixer. So the leakage is going to remain in baseband. And another difference is that on the NRF, we had an internal amplifier which amplifies the leakage before it's transmitted. While in the RFSoC, this amplifier is expected to be off-band. So when we are collecting the leakage at the output of the RF interface, the leakage is not expected to be amplified. So in the first experiment, we tried to detect a leakage from the processing system. So we had the AES software implementation running on one processor on the processing system. And with a spectrum analyzer, we try to detect at the output of the RF an harmonics which will correspond to the activity of the processor. But as expected, probably because of the strong isolation between the different parts, we could not detect any signal. So in the next experiment, we try to maximize our chance to produce a leakage from the digital domain that could reach the output of the RF. And to do this, we used ring oscillators that we implemented in the programmable logic. So ring oscillators are an infinite loop which integrates an inverter. And then the signal in the ring oscillator is expected to toggle as fast as it can go through the loop. And when we implement an important number of ring oscillators in the programmable logic, we expect them to produce a noise that we could detect at the output of the RF. And with this setup, we could detect a signal that depends on the number of ring oscillators that we activate inside of the programmable logic. So with this experiment, we could demonstrate that despite the very strong isolation between the digital and the RF, it is still possible to produce a leakage that reaches the output of the RF. And for example, we could use this to produce a covered channel. For example, if an attacker wants to exfiltrate information without having access to a legitimate input-output interface. After this, we tried to perform a side channel attack. So we implemented an AES on the PL. only one AES was not enough in order to produce a leakage that we could detect at the output of the RF. So in order to increase the leakage strength, what we did is we implemented 8 groups, each containing 12 AES. And when all the AES are activated, we can detect a signal at the output of the RF. Then we collected this leakage and we performed the t-test and we look at the minimal number of traces that we need in order to have a positive t-test. With all the AES activated, we need 150 traces in order to have a positive t-test. And as we reduce the number of groups that are activated, so we reduce the number of AES that are running, of course, the number of traces that we have to collect increase. And when we reach a realistic attack with only the initial AES that is running, even with 200 million traces, we do not succeed to have a positive t-test. So on this work, we did not succeed to have to mount a successful attack, but we demonstrated that despite the very strong isolation between the digital and the RF, it is still possible to have a leakage that reaches the output of the RF. It means that on much lower IoT devices, even if we include countermeasures in order to protect the RF from the digital, now we can highly expect that the leakage will still be present. So to conclude on this work, we are first under the difficulty to collect traces at a distance. We propose new methods that allow to collect traces in more realistic scenario. Then we have studied the frequency diversity property of the leakage, and we demonstrated that the leakage is not only present at the harmonic, but also at non-harmonic. This is very convenient to keep the tech feasible in polluted environment. And we use also this result to propose new attacks that combine multiple frequencies to reduce the number of traces. And also, with this, we succeed by combining all our contributions, we succeed to mount the attack at a distance of 30 meters. Finally, we study this attack on a different device than the NRF, and we succeed to detect a leakage. So all of this work has been presented in different papers. 2 of them have already been published, and 1 is about to be submitted very soon. And this work opens many perspectives. The first one is because we demonstrated that the leakage is also present at non-harmonics, it could be interesting to propose a method in order to detect in an unknown environment what are the best frequency to mount the attack. So an attacker, for example, could scan the environment in order to detect the frequencies where the leakage is present. Then concerning frequency diversity, frequency combination, we demonstrated that combining multiple frequency allowed to improve the attack performance. But now we could try to optimize the improvement of the attack by proposing new methods, for example, method based on deep learning. We could also try to combine frequency and spatial diversity. And finally, on the RFSoC, we did not succeed to mount an attack by analyzing the amplitude of the leakage, but we could try to search for new leakage vectors. For example, we could look at analog characteristics like total harmonic distortion, and we can look how these analog characteristics are impacted by the digital activity. And by if they are impacted, then we could try to mount new attack using these characteristics. So this concludes my presentation. I thank you for your attention, and now I'm here to answer your questions.